structure. Which structure is more stable? So it can be also decided on the basis of the formal charge. So how we can calculate the formal charge? So there is formula that formal charge can be calculated valence electron minus non-bonding electrons minus half of the bonding electron. So this is a formula which can be used to find out the formal charge of each atom in a molecule. Valence electron minus non-bonding electron, which you know, lone pair of electrons, and minus half of the bonding electrons. For example, we have an example of H3O, you know that. Example of H3O. Okay. Now for each hydrogen atom, for example, for each hydrogen atom, what will be the formal charge of the hydrogen according to this formula? So how many valence electrons with hydrogen? 1. How many non-bonding electrons with hydrogen? No. So we can say 0. And how many bonding electron is with hydrogen? How many covalent bond in hydrogen can form? Only 1. And so we have 2 electrons. So we can say half of 2. Half of 2. So we have 0 charge on hydrogen. 0 formal charge on hydrogen. Similarly, for oxygen, formal charge for oxygen. So you know how many valence electrons are there with oxygen? 6 minus. How many lone pair of electrons with oxygen? Now in this situation we have only 1. So we can say 2 electrons. And how many bonding electrons are there? So 3. So 1 half of 6. So this is, we can say, plus 1 charge. So plus 1 charge is on oxygen and 0 charge on 3 hydrogen. And the total charge on the molecule is 0 or plus 1, that is equal to plus 1. 0, 3 zeros plus 1. Okay, so you can calculate the formal charge on the basis of this formula. Valence electron minus non-bonding electron and minus half of the bonding electron. Now we can decide about the stability of the molecule on the basis of formal charge. So for example, if I take the example of a molecule like this one, so we can say stability and formal charge. Okay. For example, I have this kind of molecule. Suppose this one is, you can say this is A molecule. Another form is this is B molecule. And another form is this is C molecule. Now how we can predict which one is the most stable molecule? So this can be predicted on the basis of formal charge. So in the molecule having least formal charge, or we can say the molecule in which the atoms have formal charge closest to 0 will be considered the most stable. So first of all, we have to find out the formal charge of these molecules. For example, if we take the formal charge of nitrogen, formal charge of carbon, and formal charge of sulfur. So in this molecule, what is the formal charge of the nitrogen? So you can say that we have 5 valence electron minus how many non-bonding lone pair of electrons? So we have 4 minus half. How many covalent bonds nitrogen produces in this molecule? So we have 4 bonding electrons. So if we take, if we calculate, so the final result will be -1. Similarly, for carbon, how many valence electron? 4. How many bonding electron? 4, and minus half of 4. So you will get -2. You will get -2. Similarly, for sulfur, how many valence electrons are there? 6. How many non-bonding electrons? 0. How many bonding electrons? So we can say 8. So the final result is +2. And if you calculate the total charge, it will be equal to -1, because the -2 and the +2 will be cancelled out. For the next molecule, how many, what is the formal charge for the nitrogen? So you can say maybe the same, because both have the same structure. So 5 minus 4 lone pair are non-bonding electron, and minus half of 4, so that is equal to -1. Okay. For this one, for carbon, so we can say 4 minus 0 minus half of 8, and that is the bonding electron, and you can say 0 formal charge. For the sulfur, we have 6 minus half of 2, and that is equal to minus half of 4, minus half of 4, because there are 4 bonding electrons. And we can say the charge is 0, and the net charge is -1. For the last molecule, 5 minus 0 minus half of 8, and that is equal to +1. For carbon, 4 minus, we can say 4 minus half of 4, and that is equal to -2. And for the last one, sulfur, we have 6 minus 4 minus half of 4, and that is equal to 0. Now you can decide which molecule has a formal charge on atom closest to 0. We can say this B molecule has the atoms with the formal charge closest to 0. It means that this molecule is most stable molecule. So if you know about formal charge, you can predict about the stability of the molecules. Okay. Now we will discuss the last topic, that is the breakdown of the octet rule. The breakdown of octet rule. What is the meaning of breakdown? Means that octet rule cannot be obeyed or followed by some molecules. So there are 3 cases. The first one, odd number of valence electron. Odd number, molecules with odd number of valence electrons. We can take the example of molecular oxygen. Molecular oxygen. Okay. So if you want to draw the structure, the Lewis structure of the molecular oxygen, how you can draw? For example, we can say the O2. So there are this is the skeleton, valence electron. So how many? 6 plus 6. We have 12 valence electron, octet electrons. So we have 16 bonding electron, 16 minus 12. So we have only 4. So now the next step, assign 2 electrons for each bond. So we will first assign 2 electrons here, and because we have 4 electrons, so there are 2 extra electrons, so we will assign the next 2 electrons for the double bond between the 2 oxygen atoms. Now the non-bonding electron. So you know that non-bonding electron is valence electron minus bonding electron. So we have 8 non-bonding electron, and you can put 8 non-bonding electron on 2 oxygen atoms. So we have 4 here and we have 4 here. Okay. But experiment shows that there is only one single bond between the 2 oxygen atoms. According to the Lewis structure, we have 2 covalent bond between the 2 oxygen atom, but experiments show that there are only one covalent bond between the 2 oxygen atoms, and we have one odd number of electrons on each oxygen, and that is the oxygen molecular radical, and that is the bimolecular radical, biradicals, which cannot be explained on the basis of the Lewis. So this can only be explained on the basis of the molecular orbital theory. The molecular orbital theory, which you already know about that, and that is the paramagnetic nature of the oxygen as well. So this is one case in which the Lewis cannot explain the bimolecular radical of oxygen. The next one, octet Depletions molecules. Octet Depletion molecules. It means that the molecule which has less than 8 valence electron. So that is called the octet Depletion molecule. Molecules with less than 8 valence electrons, octet electrons. So you can say the octet electron because it cannot follow the octet rules. For example, we can take the example of the BF3. Now, according to the Lewis structure, how we can draw this structure? So you know that this is the skeleton, valence electron. How many valence electrons are there? In boron, 3 plus 3 fluorine, 7 valence electron. Total number of valence electrons are 24. How many octet electrons? You can say 8, 3 into 8. So we have 32 valence electrons. How many bonding electrons? So we have 32 minus 24. So we have 8 bonding electrons. Now assign 2 electrons for each covalent bond. So this is 1, this is 2, and this is 3. Now we have 2 extra electrons. So we should form one double bond. And you can say this is the double bond. Okay. The last step is the non-bonding electrons. So the non-bonding electrons will be calculated on the basis of the valence electron minus the bonding electron. So how many there? So we have 16. And you can say 3 lone pair here, 3 lone pair here, and 2 lone pair here. So 6 and 2. So we have 6 and 2. You can say for 16 lone pair of electrons. But experiments show that all of the bonds between the boron and fluorine are single. That means that we have this kind of structure. Experiments show that all of the boron-fluorine bonds are single. So we can explain this on the basis of formal charge. You can explain this. So you can calculate the formal charge for this molecule and you can calculate the formal charge for this molecule. So the molecule with the formal charge of each atom closest to 0 will be considered the most stable and the most correct structure. So you can calculate. For example, if you want to calculate the formal charge for this molecule, so how you can calculate? For example, okay, so we have two kind of molecule. This one and this one. Okay. So now in this situation, we have two kinds of bonds, BF double bond and BF single bond. So formal charge for boron is, can we calculate it? Boron has 3 valence electron, no lone pair, and half of 8. So how much? You can say. This is -1. For formal charge for double bonded, single bonded fluorine. Single bonded fluorine. What will be the formal charge for these two? You can say valence electrons are 7 or 6 and 6 are the lone pair of electron minus half of 2. So we have 0. Formal charge for double bonded fluorine. So you can say 7 valence electron, 4 lone pairs of electron and half of 4. So you can say +1. But in this situation, for boron, we have formal charge boron will be 3 minus 0 minus half into 6. So 0. Formal charge, because all of the boron and fluorine bonds are single, so we can take directly for fluorine and we can say 7 minus 6 minus half of 2. So you can say 0. So there are 0 formal charge on boron as well on fluorine. It means that this structure is more stable and this structure is according to experimental results. The last one is topic is expansion. So octet expansion, we can say octet expansion. The third case, case 3, octet expansion. So octet expansion means molecules with more than 8 octet electrons. And this always takes place in the molecule where the n is equal to 3 or greater than 3, which means that n is the principal quantum number, which means that the d orbital is now involved. And this octet expansion is also due to the involvement of the d orbital. For example, let me take the example of let me take this example. So how we can draw the Lewis structure for this molecule? Okay. So this is the skeleton, valence electron. How many valence electron? You can say we have 6 valence electron for chromium plus 4 into 6 electron for valence electron for oxygen, and we should put 2 here because we have 2 negative charge on the molecule. So the total are 32. Octet electrons 8 plus 4 into 8. So we have 40 octet electrons. Bonding electrons 40 minus 32. So we have only 8 bonding electrons. So assign 2 electrons for each bond. So we assign here 1, 2, 3 and 4. Non-bonding electrons. So non-bonding electron can be calculated from valence minus bonding electron, and that is equal to 24. And you can put we have 4 oxygen and we have 32 bonding electrons. We can distribute it on each oxygen atom. Okay, but experiments show that okay. Experiments show that the carbon, chromium and oxygen bond is not single, not double. That means it is in between the single and double. Now to test this molecule, we can take the help of formal charge. So it means that if the molecule has half of chances of single covalent bond and half of chances of double covalent bond. It means that we can write this structure as in this form. So half of the bonds have the chance of single covalent bond and half of the bond have the chance of double covalent. Now we can test this on the basis of the Parmar charge. So, for example, if we take this, we can calculate the Parmar charge for this molecule. So, for example, the Parmar charge for chromium, we have 6 valence electron, no non-lone pair, non-bonding electron, minus half of 8. We can say 12. We have 6 covalent bond formed by the chromium. So now the result is, we can compare these two. Okay, so the first structure is and the next structure is okay, now we can compare both. So for the first one, in this situation, the Parmar charge of chromium, valence electron minus no lone pair of electron minus half of 8. So we will get plus 2 charge. Similarly, for each oxygen atom, we have 6 valence electron, 6 bond lone pair, and half of 2. So we have minus 1 charge. And the net charge is, we can say that the net charge is plus 2 plus 4 into minus 1. So we will get minus 2 charge. Now for this molecule, Parmar charge for chromium, 6 minus 0 minus half into 12. So we will get the plus 2. You will get 0. This is 0. 6 minus 6 is equal to 0. Now we have two different kind of chromium oxygen bond. One is, so Parmar charge for the single oxygen single bonded, and Parmar charge for oxygen double bonded. So now for oxygen single bonded, we have 6 valence electron minus 6 lone pair minus half of 2. So this is equal to minus 1. Now for the double bond, we have 6 minus 4 minus half of 4, and we will get minus 2. So the net, we will get the, 0. We will get the 0. Now you can decide about the correction of the structure on the basis of the Parmar charge. Now in this situation, we have more Parmar charge on each atom, while in this situation we have less Parmar charge on each atom, which is closest to the 0. It means that this structure is stable while this structure is not stable. So this structure is correct, and which is also explained according to the experimental results. And this structure further predict about the resonance, which is another topic which we will discuss in the next lecture. I hope you will enjoy this lecture a lot. And if there is some questions, you can ask questions, and I hope I will try my best to answer. Thank you for your patience.